I want you to picture this scenario for a second. You're setting up an AI to help you with a massive multi-month project, right?
Right.
And on day one, you sit down and you feed it all your rules, your personal preferences, the strict guidelines for how you want the deliverables formatted. And it gives you that really enthusiastic, digitally eager response. It seemed to get it perfectly.
Oh, yeah. They always say they understand.
Exactly. Yeah. But then by day three, it is like that first conversation never even happened.
It's completely gone.
Yeah. It's making beginner mistakes. It's completely ignoring your guidelines. And you find yourself literally copying and pasting the exact same instructions you gave it 48 hours ago. It is incredibly frustrating, But why does AI have such terrible long-term memory? And more importantly, if we are moving toward a world of AI agents, how do we actually fix it? So welcome to the Deep Dive.
Glad to be here.
Today, we are looking at a foundational state-of-the-art paper in generative AI that aims to solve exactly this problem.
Yeah, and it's arguably the biggest bottleneck in the field right now. I mean, the paper we're exploring is titled Automatic Ontology Construction, using LLMs as an external layer of memory, verification, and planning for hybrid intelligence systems.
A bit of a mouthful.
It is, yeah. It was authored by Pavel Solovsky and Ilya Gorchkova. And what they are proposing here isn't just like a small patch or a minor software update. It is a fundamental architectural shift in how we build these systems from the ground up.
Okay, let's unpack this. Because right now, standard AI memory, what the industry calls RAG, or Retrieval Augmented Generation, is essentially just a search overlay.
Right.
It just grabs chunks of text based on how similar they are to whatever prompt you just typed. But this paper explores what they call a neurosymbolic architecture. And the goal is to shift AI from just being a really impressive predictive language engine to being a true knowledge machine that uses structured ontological graphs.
Exactly.
So I want to start with the core of the problem here.
Yeah.
If we already have R, why is it failing us the moment a task gets complex?
Well, to understand the failure, we really need to look under the hood at how standard ARG actually handles your data. When you feed a 100-page document into a typical RI system, it doesn't read it the way you or I do.
Right.
It basically takes a digital cleaver and chops all that text up into little chunks. Then it turns those chunks into embeddings.
Embeddings meaning?
Think of embeddings as mapping words onto a giant, invisible, multidimensional grid. It places concepts that frequently appear together closer to each other on this grid.
Oh, I see. So it's essentially turning language into pure math, like geographic coordinates almost.
In a sense, yes. That's exactly it. So later, when you ask the AI a question, the system plots your question on that same mathematical grid. It draws a circle around that spot, grabs whatever text chunks are geographically closest in that vector space, and just pulls them into the AI's context window.
So it's retrieving purely by mathematical similarity.
Precisely.
And I can see why that works for simple trivia. If I ask for the capital of France, the words Paris and France and capital are all clustered together in that space.
Yeah, they're right next to each other.
But as your data volume explodes or your project gets complicated over weeks, I imagine that method just completely breaks down.
Oh, it falls apart spectacularly. Because while proximity on a grid is great for finding similar keywords, it utterly fails to reconstruct the actual relationships between those chunks. It loses the rigid rules, the dependencies, the causality. I mean, there's a brilliant reference in our sources to an article by P. Solovsky called From Text to Knowledge.
Right, I saw that.
Yeah, and the author points out a crucial difference between machines and humans. Humans do not store knowledge as a linear sequence of phrases. When you read a complex history book, your brain doesn't just memorize exact sentences in order.
Yeah, definitely not.
You are continuously transforming that text into an internal structure. You track who did what to whom, what caused what, the whole chronological timeline.
Standard RG sounds exactly like a student who is just cramming index cards the night before a final exam.
Oh, that's a great way to put it.
Like they have a keyword on the front and a definition on the back. If you prompt them with the exact keyword, they can recite the fact perfectly. But if you ask that same student to write a cohesive essay analyzing how all those historical events interacted to start a war,
They completely blank.
right, they completely blank. They have the raw data, but they lack the relational understanding. Which actually makes me wonder if large language models have these massive neural networks and are so incredibly smart on their own, why do we even need external memory systems? Like, why can't the AI just live and reason inside its current context window?
Well, that really depends on the ambition of what you want the AI to achieve. If the task is isolated, like, say, drafting a quick email or summarizing a single PDF, the context window is plenty. The model can hold everything in its short-term memory just fine.
Yeah.
But we are moving toward multi-session memory. We want agentic systems that operate autonomously over weeks, systems that build detailed, evolving user profiles and execute real-world planning.
The big stuff.
Exactly. And for those applications, short-term memory weakness is fatal. The literature clearly shows that purely autoregressive LLMs, meaning models, trained simply to predict the next most likely word-face systematic fundamental difficulties in planning tasks.
Wait, really? Like, they literally can't do it.
They literally cannot look far enough ahead or remember far enough back to execute complex strategies without some kind of external memory.
Wow. Okay, so if vector similarity is just cramming flashcards, what does true AI understanding actually look like? This leads us directly into the narrow-symbolic fix proposed by Solosky and Gorshkova, which they call the dual memory architecture.
Right, so the architecture is built on the premise that a single type of memory just isn't enough. You need two distinct complementary systems working in tandem.
Memory 1 and memory 2.
Exactly. Memory 1 is the vector store we just talked about. It's fast, it uses those distributed mathematical embeddings, and it is excellent for quickly recalling vast amounts of messy, unstructured text. But the real breakthrough is the introduction of Memory 2, the RDF and LWL graph.
Right, and RDF and OWL being standard frameworks for structuring data on the web.
Yeah, they are. This is the structured symbolic memory. So instead of storing loose chunks of text, this graph stores explicit entities, their concrete relationships, their rigid classifications, and logical constraints.
Okay.
So when a user asks a complex query, the system doesn't just do a keyword search. It actually fuses data from both memories. It runs a vector retrieval to find the relevant text context, but it simultaneously runs a SparkQL query.
Oh, wait, query.
SparkQL, it's a specialized language for navigating graphs. So it runs that to extract the explicit logical rules governing those specific concepts.
Let me try a real-world analogy to map this out. This dual memory system sounds exactly like a classic noir detective's office.
Okay, I like where this is going.
So the vector store memory 1 is the massive, overflowing filing cabinet full of witness transcripts and police reports. It's incredibly text-heavy, and you can flip through it quickly to find a specific quote or a name.
Right.
But the ontology graph memory 2 is the giant corkboard on the wall with the red string. It physically and visibly connects the suspects to the motives, the locations, to the timelines. It is entirely structured and relational.
Yes. What's fascinating here is that in this system, the concept of ontology as memory is no longer just some academic metaphor. It means the system is actively extracting changes in the state of the world.
It's updating the corkboard.
Exactly. It is constantly updating its internal model to reflect who is related to whom, when that connection happened, and under what specific conditions. It completely separates the simple recall of text, the filing cabinet, from the actual semantics, constraints, and explainability that the corkboard provides.
Right.
But you can't just have two separate memories sitting there in isolation. They have to talk to each other, which requires an orchestrator.
Right, a conductor for the orchestra, essentially.
Right. Yes, and the authors utilize something called the Model Context Protocol, or MCP. Think of it as a highly efficient universal switchboard operator.
MCP, got it.
It uses a standardized communication format to orchestrate the LLM, the vector database, any external APIs you might be using, and that structured graph. But the MCP doesn't just blindly pass data back and forth. It actually routes information through a critical validation layer. They employ shape validators, specifically SHACL, to ensure structural correctness, alongside reasoning engines to handle logical consequences.
Okay, shape validators. Give me a sense of what that actually means in practice.
Think of a shape validator like a bouncer at a very exclusive nightclub, but instead of checking IDs, it's checking the logical shape of reality.
Oh, I love that.
Right. So if a new piece of data tries to enter the graph claiming that a human being was born in the color blue, the validator looks at the shape of what a human profile should be. It says, wait a minute, the birth attribute requires a date or a location, not a color. This fundamentally violates the structure. Access denied.
So it keeps the graph logically sound.
It's exact.
Okay, I'm fully tracking the detective's office now. We have the filing cabinet, the switchboard operator, and the bouncer protecting the corkboard. But I keep getting hung up on the logistics of the corkboard itself. A massive web of red string is completely useless if a human engineer has to stand there and manually pin up every single connection between billions of data points.
Oh, absolutely. That would take forever.
Right. And the entire point of artificial intelligence is automation. So how does this system manage to build and update this complex, structured graph all by itself?
Well, it tackles that through the ontology builder pipeline. The paper outlines a fascinating pipeline for how an LLM can automatically construct this from raw data, acting almost like an automated, hyperpedantic librarian. First, the system ingests heterogeneous sources. It just eats everything: PDFs, database logs, your daily chat history.
Okay.
Then it performs named entity recognition. It scans the raw text and isolates the key players: the specific people, the software tools, the locations.
It finds the suspects.
Exactly. Then comes relation extraction. It doesn't just pull the nouns, it hunts for the verbs connecting them. It asks, is entity A a part of entity B? Does concept X depend on Y? Was this event caused by that action?
But wait, human language is a chaotic mess.
It really is.
What happens when I'm working on a project and I mention Apple, the tech company, in an email, but then in a personal note I save a recipe for an apple pie? Does the AI connect Tim Cook to the cinnamon?
That is a great question, and it is precisely why the next step, normalization, is arguably the most critical part of the pipeline.
Normalization.
Yes, normalization is how the system resolves homonyms, merges duplicates, and aligns conflicting terminology. And how it does this is brilliant. It doesn't just look at the isolated word apple, it leverages those vector embeddings we talked about earlier.
The grid.
Right, it analyzes the context surrounding the word. If apple is flanked by words like revenue, silicon, and lawsuit, the system confidently maps it to the corporate entity.
Makes sense.
If it's surrounded by oven, crust, and degrees, it maps it to the fruit. Normalization ensures the graph aligns. It also fixes measurement conflicts. If one document says a component is 3 meters long and an API says it's roughly 10 feet, the normalizer translates them into a single unified metric so the graph doesn't break.
Okay, so once everything is normalized, it actually builds the connections.
Right. It serializes the data into machine-readable triples. Subject, predicate, object. Company X acquired startup Y. Once serialized, it hits that rigorous validation stage we discussed, the bouncers checking the structural shapes and the logical reasoning.
And it passes.
If it survives all of that, it gets written into the final RGF format, which allows for version control, and it's officially published to the graph database. And the best part is, this isn't a one-time setup. It's a continuous feedback loop. Every time you interact with the system, your dialogue is reprocessed. New facts are extracted, validated, and added to the trusted graph.
Okay, I have to stop you there and push back on this underlying premise for a second.
Go for it.
We are using a large language model to extract these facts and build this ontology. But anyone who has used an LLM for more than 10 minutes knows they hallucinate.
Oh, constantly.
They confidently invent things that just aren't true. So aren't we just using a fundamentally flawed, hallucination-prone system to build its own factual foundation? How is that not a recipe for total disaster?
It's a really fair point, and it's actually the most common critique of neurosymbolic systems. But the authors anticipated it. That is exactly why the architecture relies on a strict two-loop system. In this framework, generation is entirely divorced from verification.
Interesting.
When the LLM reads a document and extracts a new relationship, the system treats that extraction strictly as a hypothesis. It does not go straight onto the corkboard. It has to face the SHACL and OWL bouncers.
So the hallucination gets caught at the door.
Precisely. If the LLM hallucinates a fact that violates the existing structural rules or logical constraints of the established ontology, the fact is rejected, it gets quarantined.
Wow.
It stays in the background log so human operators can audit why the AI got confused, but it never infects the trusted graph. This approach actually mirrors some really interesting research by Belkak and colleagues regarding specialized agent layers. You don't ask the massive creative LLM to govern the logic. You use smaller, specialized operational models to handle the rigid verification tasks, while the main LLM acts purely as a creative engine. The architecture essentially forces the system to logically filter its own hallucinations.
Okay, I mean, on paper, that theory sounds incredibly robust. But a brilliant architectural theory is just a theory until you stress test it. Does this neurosymbolic approach actually move the needle in practice? Let's look at the empirical evidence the authors provided. They started with a classic benchmark of logic and planning, the Tower of Hanoi.
Yes, the Tower of Hanoi. It's a famous mathematical puzzle. You have 3 vertical pegs and a set of disks of different sizes stacked on the first peg. The goal is to move the entire stack to the last peg. But there is a strict physical constraint. You can only move one disk at a time, and you can never, ever place a larger disk on top of a smaller one. It is a pure, unforgiving test of multi-step planning and reasoning about a changing environment.
And language models notoriously despise this puzzle. They can't, see the board state as it changes.
They struggle immensely. The authors ran a quantitative test comparing a baseline LLM, specifically Qwen3 Max, against that exact same model, augmented with their Ontology lab layer. At a low complexity of 3 disks, the baseline success rate was 26.3%. With the Ontology acting as its memory, it jumped to 33.3%.
So a decent 7 percentage point increase.
Yeah, a nice bump, but not earth-shattering.
Right.
Then at 4 disks, they actually hit parity. Both systems succeeded exactly 33.3% of the time, but at 5 disks, the dynamic dramatically shifts.
Oh, really?
Yeah, the baseline model stayed stuck at a 33.3% success rate, but the ontology-backed system leaped forward to a 45.5% success rate. That is a massive 12.2 percentage point improvement over the baseline. And just for full transparency, at 6 disks, the complexity was so high that both systems completely failed, hitting 0%.
They both broke.
Exactly. I do want to note a slight limitation in the paper, though. The authors didn't disclose the exact prompt temperatures or the total number of evaluation runs. So scientifically speaking, we have to treat this as highly descriptive architectural evidence rather than a finalized statistical proof. But the pattern it reveals is undeniable.
Here's where it gets really interesting to me. Look at that middle zone, the 5 disks. It's like cooking, right?
Cooking.
Yeah. So solving a 3-disk puzzle is like making a grilled cheese sandwich. The baseline LLM can mostly handle it, and the ontology-backed AI can handle it. Solving 6 disks is like asking someone to cater a 500-person wedding blindfolded. It is so overwhelmingly complex that both systems completely collapse.
That's a great analogy.
But 5 disks. 5 disks is like cooking a complex, multi-course Thanksgiving dinner. This is the exact complexity threshold where the baseline LLM, trying to just improvise from its context window without a solid recipe, completely falls apart. But the AI equipped with an ontology, an AI that has a structured, explicit map of dependencies and constraints, really shines.
The Thanksgiving analogy is spot on, because an ontology gives the AI a persistent state to reference when the steps start overlapping. And we see this exact same dynamic, the reliance on hard rules over improvisation, play out in their qualitative evidence, which focused on strict regulatory compliance.
Right, the fact analyzer test.
Yes. They subjected the system to an incredibly specific, nuanced FDA regulation regarding clinical trials.
Okay, I have the prompt they used right here, and it is a total mouthful of legal jargon. They essentially asked it, can a sponsor initiate a clinical investigation if the FDA hasn't sent written approval for their investigational new drug application, assuming a 30-day period has expired since submission, and the FDA hasn't explicitly placed a clinical hold?
I mean, just listening to that is exhausting.
It's the kind of convoluted sentence that makes your eyes glaze over.
And it is precisely the kind of sentence that trips up probabilistic language models. When they ran this prompt through the standard LLM, it confidently generated a negative answer. It basically said, no, the sponsor must wait for explicit written communication from the FDA before proceeding.
And the grading system strictly flagged this as contradicted.
Exactly. Why? Because the LLM hallucinated a restriction that simply didn't exist.
But it hallucinated it because it sounds incredibly plausible. Like if you ask a random person or an AI trained on human caution, should you start a medical trial without written FDA approval? The safest, most logical sounding answer is, no, definitely wait for the paperwork. It's predicting the language of bureaucracy.
Exactly. It leaned entirely on general linguistic plausibility. But the AI equipped with the ontology graph provided a structured yes, because it wasn't guessing what sounded right, it was traversing its graph. It specifically cited the exact Rule 21 CFR 312.40, which explicitly states that an IND application becomes effective by default after 30 days if there is no clinical hold notification. The active absence of a hold constitutes legal permission.
So the standard LLM confidently invented a safe-sounding restriction, but the ontology system actually went to the filing cabinet, followed the red string on the corkboard, and check the literal rulebook.
Precisely. This perfectly illustrates how verification in this architecture completely changes. It isn't based on the general plausibility of the generated text. It is based on specific encoded rules and applicability conditions. The entire operational cycle of the AI evolves. Instead of just generating text and hoping it's right, the cycle becomes a 4-step process.
Proposal from the LLM.
Right. Then a symbolic check against the ontology graph. Then an internal repair if the proposal violates the rules. And only then, execution of the answer.
That's incredible. So what does this all mean for you, the listener? Whether you are a developer trying to build a personalized AI tutor that actually remembers your specific learning style week after week, or an automated researcher synthesizing scientific papers, or just a user who wants an AI agent to handle your impossibly complex calendar pure text prediction, just doesn't going to cut it anymore.
So really not.
It needs this structured memory graph to truly understand your world and hold on to it over time. The ontology transforms AI from a machine that just probabilistically guesses the next word into a machine that actively updates a mutable, interpretable model of reality. It is the key to enabling stateful agents that can interact with the real world, whether that's navigating legal contracts, understanding technological constraints, or coordinating with the actions of other agents.
Yeah, and if we connect this to the bigger picture, this neurosymbolic approach is the bridge bringing us significantly closer to stronger forms of AI with truly explainable reasoning. When this AI makes a decision, it isn't a black box. You can physically trace the exact semantic path it took through the graph to reach its conclusion.
Right.
But, as the authors candidly note, there are still very real engineering limitations to overcome before this is everywhere.
Yeah, the paper makes it clear this isn't a flawless magic bullet just yet.
Far from it. They highlight the persistent challenge of schema drift.
Schema drift.
Yeah, the real world changes, and the ontology structure needs to evolve with it, but sometimes it gets out of sync. Without constant, rigorous normalization, the graph can degrade into what Solowski terms sophisticated chaos.
Well, that sounds bad.
It is. There's also a significant latency issue. Running heavy logical reasoning passes through complex graphs takes time and serious compute power. It's not instantaneous like simple text generation. And crucially, at least for the foreseeable future, we still need a human in the loop to govern the highest levels of the schema and ensure the fundamental rules aren't breaking down.
So we still need the human detective walking into the office every now and then, looking at the corkboard and making sure the AI's web of red strings actually reflects reality.
Exactly.
And honestly, that leaves me with a final, slightly provocative thought, directly inspired by that idea of sophisticated chaos and schema drift. We've established that this system relies heavily on filtering out new facts that violate its existing logical shapes. It runs everything past those bouncers, the SHACL validators.
Yeah.
But what happens if this automated pipeline accidentally locks in a structurally valid but fundamentally incorrect worldview very early on in its training? If it uses that flawed foundational premise to filter and reject all future incoming facts, simply because they don't fit the shape of its initial error, could an advanced AI effectively trap itself in an impenetrable echo chamber of its own logical perfection?
Wow.
It might be perfectly consistent, but entirely wrong. Just something to think about the next time you ask an AI to definitively tell you the truth.
A fascinating dilemma for the future of knowledge engineering.
Thanks for taking this deep dive with us. We'll see you next time.